think it's better that you have more time. But on the other hand, there's another reason, and that's that one of my jobs as a professor is to guide you. Well, Catherine is joining us remotely, okay. One of our goals, one of professor's goals, is to guide you towards being a professional. And so this is a part of guidance that's not about instructing you on the topic of the course. It's on instructing you on how to do a better job that is the kind of job that's expected of a professional, okay? So the kind of job that's expected as a professional is one, for example, where the homework responses are always typed up and you have spell checked your work, and the references that you use are professional references and they're normally not websites, okay? And so when you get your homework back from me, as long as it's in Word as opposed to a PDF, and you can do either, but with a Word document, I can correct formatting, I can show you a useful way to format things. I require of my research group a certain style of formatting, and I'm going to do that for you, and you don't have to, when you walk away from the course, use this. It's just one that in my experience is valuable, okay? And the idea is to give you an idea of how careful you should be in preparing any kind of document that somebody else is going to see, okay? And that's really the reason for this part of the course, which is something I would do for you no matter what the course, okay? I'll correct your English. I will, and I understand that for a number of you, English is a second language, all right? And so that's something that is also part of my job, is to help you come up to speed, okay? So with that in mind, then I would rather that you took more time with the homework and do a better job, with the idea that by getting in the habit of doing a quality job, you will do that in the future, no matter who is asking for whatever, okay? And that leads to, of course, a better job sometimes, or better communication skills. So in fact, one of the things that I like to say, and I say it to my students, but in class it's also valuable, you can go very far by being a good scientist. But if you cannot communicate, or researcher, or engineer, if you cannot communicate very well, then people will not respect what you've done as much as if you also have good communication skills. Now, the reverse is also kind of problematic. A person who is very good at communicating can go a lot farther with mediocre engineering than someone who's poor at communicating but excellent in engineering or research. There's something else to be said, and that is that sometimes, unfortunately, you have to be very proactive, meaning you have to go out and reach out and do things that are not expected of you. This also comes to having reports that are of highest quality, so that you are impressing whoever is reading them, or you're planning to impress whoever is going to read them, by the attention that you pay. Okay, so I met a guy who was very quiet, and he was kind of like in a tiny little place. And when I talked to him, he was absolutely brilliant. Okay, and I went away with an incredible impression. And I wondered why he ended up in this tiny little place. But he was happy and competent, very competent. But he ended up, because he was so competent, he won the Nobel Prize in chemistry despite not wanting to talk about anything. But this is not always the case. Okay. So with that in mind, now I'd like to get on with the show, so to speak. And I want to bring us back to this slide. Okay. This is basically understanding diffusion of ions in electrolytes. That's the picture we're working on today. And I could talk about the microscopic picture and I can talk about the nanoscopic picture, but indeed, understanding the atomic picture is probably the best. So we're interested in understanding how lithium ion diffuses, but it could be a sodium ion or magnesium ion. Those are the ions that we're going to spend more time on, okay? And the take-home message is that the typical diffusion constant, D sub 0, is dependent on viscosity, the Boltzmann constant, and diffusion coefficient. You know, well, the radius of the solvating ion, or the solvated ion is what it really should be. So we need to understand that movement in any lithium battery is dependent on those things that affect the lithium, sodium, or magnesium ion. And to understand those is to understand sometimes the key factors in how to develop better materials, better solvents, okay? So that's, this you already saw, and this you saw. Right, one thing I want to talk about here to remind you is we need to solvate lithium ions, and we need to separate the lithium ions from their counter ions. And there are many ways to do this, but, oh, I'm sorry. I thought I turned that off. Okay, so the important thing is the dielectric constant. The dielectric constant here is really low. Okay, if we think about water, water's dielectric constant is 80. So we're going to think about this in a different way in just a little while, because it gives us an understanding and a perspective of solvation at lithium ions. Okay, so now going back to basics, this is something you've seen already and you had a homework question on it. So we can understand the driving force in a battery as a difference in potential between the material that's easily oxidized like lithium or sodium or magnesium, and that which is easily reduced, which is something like oxygen or sulfur. And of course you could talk about halogens, but they play almost no role in batteries. All right, so the free energy difference comes from the free energy of formation of the various elements, and the difference is really the redox potential between them. All right, and so this is the free energy of reaction is minus ZFE, right? E is the voltage between the electrodes, okay, which is something you now understand. All right, now we are going to talk about, and we've already talked about to some extent, the chemical potential, because the chemical potential is related to the free energy, but usually the chemical potential is much less than the free energy. And the reason is because all of those things around the anion and cation that control its behavior, okay? And that's what we're concerned with. So we can mathematically understand the relationship of the free energy in the system or the chemical potential as being the sum of the free energy of each element, okay, each phase J, all right, and in this case, the partial for the mole fraction, okay? So you sum all of these and you, in principle, get the chemical potential for the system, okay? But the chemical potential, when you sum it, is not unity because there's other issues here, okay? Because chemical potential depends on all of those things that affect the cation and the anion, okay? And the chemical potential is species related. And then we also have, so it's chemical potential of the ith component is the ith component 0 plus RT log of AI, which is the activity. So the activity, if it were perfect, if the ions were absolutely solitary and unsolvated and moving in a vacuum, would be kind of 1. Right? They're not. Right? That's our problem. That's our basic atomic picture that needs to change or needs to be assessed. Okay. So let's look at the solvation sphere of a lithium ion. And we can talk about water. And then we can talk eventually about organic liquids. So this is a time for me to talk about something a little different than this, and then we'll come back to this. How reactive is lithium metal? Pretty reactive. Okay, so lithium metal in air will oxidize. If you're not lucky, it will oxidize by bursting into flames. Okay. This is true also for sodium. And magnesium is less likely to oxidize. Okay, but maybe you have seen magnesium flares. Magnesium flares are bright white and they work underwater. Okay, so the reactivity is very high. All right, so now in a separate but important, relevant idea, if I have water anywhere in my battery, guess where it's going to wind up? It's going to wind up reacting with lithium. Then it's going to wind up forming lithium hydroxide and hydrogen. So water is always going to be a bad actor. Do you think we can do away with water? No, we can't. Okay, that's a problem. So what you're going to assume is that there's going to be trace amounts of water, even when you process in a dry box. It's not water per se, but surfaces will not have water, they will have OH. Okay. So that means that that OH is a source of water or source of hydrogen, source of reactivity. And you just have to live with the fact that some of it exists. And it's possible under some conditions to eliminate the hydrogen by pre-reacting it with something else. That's another step. All right. So those are things that we will talk about. Okay. So I just wanted you to understand that water is ubiquitous and we're not going to always have a way to deal with it. But now this also comes to another ubiquitous thing. All of the time, we're going to talk about lithium salts, and we're going to talk about sodium salts. Magnesium salts are going to be a sort of an exotic thing. So we'll spend less time with that. Lithium salts all react with CO2. So the byproduct of doing studies with lithium salts and electrolytes is that you can often form lithium carbonate. If you want to work with solid electrolytes, then you can also expect that the surface of solid electrolytes will have carbonate on it. So sometimes the carbonate is not as much of a problem as other times, but it does, you will see it if you do spectroscopic analysis, and you must remember that it will inflict itself on your results, meaning it's almost always going to be negative. All right, so having said that, you can remove lithium carbonate by heating it up or polishing it off. Which would you rather do for a ceramic substrate? Well, Jeff, if I have to polish something, what do I do? What kind of steps do you think I should do?
clean it off, and you use like a grit and you sand it down.
Yep. All right. So sand it down. I can't use water, right? All right. So now I have to sand it, and I have to use, if I'm going to keep it clean, then the grinding that I have to do has to be with very clean media. Okay, so guess what? That means it costs money, right? And I have to do it in a pristine, lovely word, pristine environment. So if I heat it, then I get rid of the CO2. Do you think that's easier? Should be, right? All right, so Anita, if I were to heat a ceramic, what temperature do you think I have to heat it up to decompose lithium carbonate? Well, high is a relative term. High, you don't want to be walking around in the desert at 130 degrees Fahrenheit. But what's high in terms of ceramic? 100? Hundreds. Okay. Can you be more specific? No. Okay. All right. So the decomposition temperature of lithium carbonate is 700 degrees. Oh, goodness. Do I want to heat anything to 700 degrees? Actually, to make a ceramic thin film, I have to heat it to 700 degrees, even higher. So, fine. But then after I do that, I then want to clean up the surface. So I might have to reheat it to 700. How do I do that carefully? I will give you a perspective, all right? Yesterday, or the day before, I was reading an article in the Ceramics Bulletin about catalytic converters for automobiles. Catalytic converters are monoliths with pores in them, okay, linear pores that are extruded. And those catalytic converters are produced in millions of pieces a year because they go into each car. So I met a guy who used to work for Corning, who was the producer of these catalytic converters, and he used to say that they used to sinter these catalytic converters in a rail car. So they would put a rail car full of these things into a furnace, of course, big enough to hold a rail car, and sinter them all at one time. So we could make ceramic thin films that way. And we'll come to why we might get away with that. But do we really need to heat the whole ceramic to get rid of the CO2? Come on, how many times have you cooked something and then you accidentally touched the frying pan? Right? So you only have to get the surface hot. So you could get rid of CO2 on the surface, assuming it hasn't permeated, by just flash heating. So that's easy, and you don't have to do that in a very complex manner. You can use laser heating to clean off the surface. Okay, so these are the kinds of thought processes that I'd like you to adopt here. Okay, so now we have a salt that somebody has left sitting in the lab for a while. And even though it's sealed, if it's a very humid Michigan summer, some water will probably get in. And so you'll solvate the salt a little bit. So this is a water and salt. So water and salt, right? So this is a picture, this is a lithium ion, this is a counter ion, anion, all right? So we know that water is polar, E is the dielectric constant. So not only is it all the oxygens of the water around the lithium, remember, the lithium is like a point charge, all right? It's very tiny, okay? So now we see that this is kind of solvated, and you can see the cations are sharing anions, all right? And now the oxygen is got is well, it's electrochemically, it's electrically negative. It's a negative dipole, right? So you can imagine that there's a bunch of oxygens around here. Now, what you also might expect, which is not illustrated here, is that we should be getting hydrogen bonding to the anion because the hydrogen is positive. Okay, keep that in mind. Now, let's move to a better solvation sphere where the salt is dissolved in water. Now we have the lithium ion, and now the oxygens are in 3D around it. You can envision there being about 6, doesn't really matter. And the hydrogens are now facing away, and the hydrogens are hydrogen bonding to waters in a second layer. So here's where our perspective needs to change a bit. The waters here are so tightly bound to the lithium that they can't move. So when this ion diffuses, for sure, the volume occupied by the ion is not that, it's that. So the rate of diffusion is defined by the hydrodynamic radius. However, because this is a point charge, it's possible that the water in the secondary solvation sphere is also strongly bound. So actually the hydrodynamic volume is probably closer to that. So if you were taking a ceramics course, you would also learn that these are called stern layer. It's not important here. But now the water at the periphery of the second layer can exchange slowly. Why are we going through this in detail? Because this is also the way we understand how to change solvation, how to change solvation in liquid electrolytes so that we optimize properties. Okay, so the other thing is the anion is sitting far away. That's good, but let's talk about applying a potential. I'm going to apply a potential. I have a plus electrode and a negative electrode. The plus electrode is going to drag anions in the direction of the plus electrode, and the other electrode, the negative electrode, is going to attract lithium, right? So the hydrodynamic volume means that the movement of this species is affecting all of the liquid it moves through, and it's a much larger structure than just a lithium ion. So it's dragging itself and the attendant solvent molecules and maybe occasionally a water outside that happens to be strongly hydrogen bonded. And then if there's a little bit of anion, it might also drag the anion even though it shouldn't go in that direction. And then you'll note we haven't talked about the anion being solvated. We'll come back to that, but the anion is also going to be solvated to some extent, and it's going in the other direction. And as a consequence, the volume occupied by both ions is larger than just the diameter of the original ion, and the friction that these ions undergo when they move is much larger. And that then, in a sense, is generating heat, which means you're losing electrochemical potential because it's going to heat. And gosh, do you think that happens in polymers and solids too, solid electrolytes too? Yep, but in a different way. So let's start by examining what it is we see in organic electrolytes and how they differ from water. So the dielectric constant of water is 80. Some of the liquid electrolytes, and we will spend some time with them, have dielectric constants of 30 and 40. So in a concentrated solution, with ethylene carbonate, or this is actually propylene carbonate, but if it were, then lithium is partially solvated, but now the tetrafluoroborate anion is within a strong interacting distance with the lithium. Even though the tetrafluoroborate is supposedly a diffuse anion, okay? So it shouldn't be strongly attracted, and that's our basis here. Should not be. But if there's no solvent, then it's going to be a salt anyway, right? So we're talking about, let's call it tightly bound. It's not really tightly bound because there shouldn't be any solvent to speak of if it's tightly bound, okay? But tighter bound than over here. Here, in this representation, you don't see the tetrafluoroborate ion. It's somewhere outside this solvation sphere. Now, in this system, we have the carbonyl acetyl bond O, right? Why is that on or near the lithium? Well, it looks like water. It's got electrons to donate to the lithium. But then you might argue, gosh, why doesn't the lithium sit here? It's got this oxygen and that oxygen. And you might argue that, yeah, it could, but it's better when there's 4 carbonyl oxygens around it. It stays better organized. Organized is something we actually don't want. We'd like it to be not like the solvent sphere in water. We'd like these carbonates, is what they're called. We'd like them to be mobile. Why would we like them to be mobile? Because that means that the order around the lithium ion is less. And that means that there's no secondary solvation sphere, and the hydrodynamic radius, which is a misnomer because hydro indicates water. The hydrodynamic radius is smaller. That means that the movement, when we have potential, is faster. Diffusion is faster, which means less friction, and we get a better system, okay? What we are not interested in is having a contact ion pair. So a contact ion pair literally has electrostatic bonds very close. The design of an anion is such that you would like it to be as far away as possible so that the lithium is free to move, but you would like to think of it this way. And this is what we'll end up thinking about when we go to polymer and then solve electrolytes. If the environment in the electrolyte is uniform, then the lithium ion moves through and doesn't experience some localization, so it's mobile. So now we have a liquid where, in principle, the lithium ion movement is such that it's not hindered by formation of contact ion pairs. So our goal in developing a very good lithium electrolyte is to have lithium movement be free, have the solvation sphere small, and of course that also implies low viscosity. So people, because of the importance of this in batteries, and because batteries are a huge business, people have spent a lot of time studying these, all right? So ethylene carbonate, propylene carbonate. So this is a lithium with 1 ethylene carbonate. We see just the carbonyl group near the lithium. Then with 2, they're opposite each other because they're as far away as possible, because then they don't bump into each other. That basically they vibrated and they all moved away because they can. And when you get 3, you get 3 equidistant in a sphere, okay? However, of course, 3 always define a plane. And now when you have 4, you can have a tetrahedron, and now they're all equidistant. So the best idea is, oh, I have 4 ethylene carbonates all compensating for the lithium ion charge. So one would imagine that of the four, they're at least partially mobile, because if one leaves, then another one can come in, but the charge is stabilized by the other three, okay? So this kind of an idea tells us something about the minimum amount of solvent we can have. We never want a lot of solvent, all right? We remember the discussion with regards to a pouch cell versus a coin cell. Okay, so with propylene carbonate, now you can have 1, all right, you can have 2, and 3, and 4, and fine. People, these are models. And they kind of exactly reflect what we talked about. The difference is the methyl group here might cause more disorder. It might be bulkier so that when they bounce against each other, they fly away more readily. And now people have looked at the difference between propylene carbonate and diethyl carbonate, and they can use something called Raman spectroscopy, okay? And they can see, and you don't have to know anything about Raman spectroscopy. I want to explain this to you because they can see that this little side shoulder here is reflected in the presence of, this is propylene carbonate and diethyl carbonate. It's representative of 1 diethyl carbonate. So this is not perfect in the compositional, it doesn't reflect the composition exactly. What we're seeing here is the average time that an equal amount of diethyl carbonate and propylene carbonate spend with the lithium ion. So now they know the mobility of the diethyl carbonate, or you could argue the solvation properties of the diethylene carbonate are not as good as propylene carbonate because the ethyl groups are there to wag around and they push the other, it gets pushed away. Okay, so the volume with the propylene carbonate is smaller and apparently more stable. All right, so at this point, we've talked about solvation. Let's talk about counterions. Some of these examples aren't perfect, and I wish that I could find more perfect examples, but the take-home message is the same, okay? So lithium ions are roughly 0.7 angstroms. Manganese ions are 0.8 angstroms. Actually, magnesium is smaller than lithium, okay, 0.6. So in principle, it represents a lovely material for a battery if it weren't for the fact that it's 2+ charged, and therefore it has much stronger solvent binding, so much stronger that you have to have special solvents that can't be these to make a magnesium-based liquid electrolyte battery. Okay, so this is the TFSI, but it's hexafluoro methyl or bis trifluoromethyl sulfoxyimide. I expect you to remember that. No, I don't. Okay. So now, what is the take-home message is a solvation sphere of the anion with respect to these two cations. So over here, we see the distance from the lithium to the nitrogen in the TFSI, the hexafluorophosphate, dimethyl carbonate, and that's the lithium oxygen over there, and the ethylene carbonate. So all of these, the carbonates, okay, oxygen distances are between 2 and 3 angstroms, 2.2, 2.3. They're pretty similar, okay? However, the lithium nitrogen distance is way over here at 4. So that means that the bulky trifluoromethyl groups push the anion away. It's better solvated, okay? And so the lithium in this system would have a solvation sphere that doesn't have a strong contact ion pair. Okay. Likewise, if you use manganese, you get the same effect. Now, the manganese is going to have 2 pentafluorophosphonates. Okay, dimethyl carbonate, they're the same distance, is pretty close because the atomic radii are pretty close. But when it comes to the TFSI, it's separated, okay? Now, these are models. They are mathematical models. They are not real crystal structures. And they show the ethylene carbonate DMC, so there's 2 ethylene carbonates here. So it seems to be, ethylene carbonate is now a cyclic guy. It's not diethyl carbonate, keep that in mind. All right, and there's ethylene carbonate, which has got, then there's dimethyl carbonates, even smaller. And now here with the PF6, it's contact ion pair. Okay, so it's strongly bound. All right, we don't want that. With the TFSI, it's a little bit bound, but not as strongly bound. This has got double bonds. And over here with EC4, which doesn't seem to have a TFSI, there is no TFSI in the picture. Manganese, TFSI is the same 1 bond versus multiple bonds with the PF6. So our idea is to design an anion that's able to stay far away or is forced to stay far away from the cation. All right, so having said that, here's our story. Do I want to use TFSI in my liquid electrolyte? There's 2 answers. Flora? I'm sorry, but you'll have to speak up. Jeff can't hear you. Can you speak up, please? Powerful, forceful. What? You might want to use it. Can you be more forthcoming than that? Mm-hmm. It will block the cation from what? With? Okay, all right. All right, can anybody suggest why I wouldn't want to use it? Yeah, it's a lot more expensive. So now, ladies and gentlemen, comes an economics lesson. Okay, this is expensive, but not too expensive. That's very expensive because you have to make the trifluoro groups and you have to put them on the sulfoxy groups. And actually, this is trifluorosulfonic acid imide, so it's not that bad, but not that cheap either. And you have fluorine in it, so if you put it in a battery, you have to figure out that you might have recycling problems. Okay, having said all that, then Jeff would whisper to all of us, yeah, but if the battery lasts forever, then I don't have to recycle it very often. Therefore, the cost of ownership is much less if I don't have to replace it for 10 years. So this is a very important factor in determining if something is useful, if the cost of ownership is very low, even though the initial price is high. Okay, so this is something we're always going to have to deal with. And it's a good answer if somebody asks you, and it's not me, okay, that you can say, well, there's 2 things to consider. One of them is the cost of ownership. So you look really smart, right? I hope. Okay, so this is a very interesting study, all right, because this is a system where you add the fluoroethylene carbonate, and in 5 and 10%, 2 molar, 5%, 10%, and here's what you see. Now, again, this is modeling. Okay, So this is now the pentafluorophosphates, and look where the lithium is. And so that means that this is a separated ion pair, or a solvent separated ion pair, SSIP. Okay, and now with two FECs, all right, it's again solvent separated with one FEC, now contact ion pair. All right, over here, when you don't have an FEC, you have, oh, look, there's two counterions there. This is a simulation, remember that. But if I have two contact ion pairs in the same structure, it means I have another lithium nearby, doesn't it? It must be to have neutral charge neutrality. So a different set of aggregates. What do aggregates tell you? What is the size of the ion that's moving through solution if you have an aggregate? It's much bigger. The diffusion rate is therefore what? It's much slower. So I do not want aggregates. So I recognize that FEC is expensive. On the other hand, if I get a 40% improvement, maybe by the cost of ownership is worthwhile. There's another reason for this, which we can't know from this slide. The presence of a small amount of fluorine will also cause the formation of a stable SEI under some conditions, solid electrolyte interface. And that is added for that reason also, is that it stabilizes STIs. We will come back to that, but that's important because this is part of our attempt to develop a detailed understanding of solvents. All right, so that's really a great start. And now we're going to talk about ion conduction in polymer electrolytes and move on to solid electrolytes. Okay, so we just did liquid electrolytes, and I think you've seen this slide before. Okay. See, one of the problems I have is that because I made these videos before class, I've seen these slides like sometimes 10 or 15 times. So I don't know what you really saw and what I saw 10 or 15 times. So please forgive me in that case. All right, so a liquid electrolyte has high energy density, excellent rate capability, but of course, you can get catastrophic failures with it. Okay, so I could replace the liquid with a polymer. Usually that means that the rate of diffusion is down, okay? So I have a problem, but I have stability and I can have some mechanical properties that, for example, prevent or limit dendrite propagation. But I could add a little bit of a liquid electrolyte to this to make a gel polymer. Now I have something that looks like a liquid electrolyte, but is formable and maybe more stable than the liquid. Okay, but it has poor mechanical properties. And then of course, we can have a solid polymer electrolyte, which will have good mechanical properties. It will be stable, but usually diffusion through polymers is always going to be slower than through liquids, right? And then finally, at the other end of the story, all solid state ceramic electrolytes. And of course, we all know that everyone wants to have an all solid state battery, so we have all sorts of issues to overcome. Okay, poor cycle performance, unstable interfaces. People are working on that, but not always. All right, so polymer electrolytes are multifunctional, they're flexible, they can have good mechanical properties. Some of them can have moderate stability, and in principle, they're safe because it's hard to burn them. All right, so this is sort of like a schematic of universal design parameters for polymer electrolytes. These are wish lists for polymer scientists. Some of these, because they can convince their boss, need to be explored. Some work has been done in this area. All right. So the simplest systems really have some use. The salt homopolymer, if you can bind the anion to the polymer backbone, then the anion can't move. This goes back to our perspective of having a uniform matrix that always has the same anionic species everywhere, so that the lithium is now moving between individual anions and the anions are not moving. That looks pretty cool, right? Because that makes sense. The issue will be how fast the lithiums can move, what's controlling their movement and so forth, all right? We can have simply got salt doped into a polymer where the polymer has solvating abilities like a liquid, but it's a polymer. Okay, this is a block copolymer. There's a reason for this, which we'll talk about in just a little while. And all of that is just a salt doped polymer where you're using a polymer as a substitute for a liquid electrolyte. Now, we have non-linear polymer electrolytes where you can make hairy polymers, okay? In principle, this is making something with higher surface area. So that means that the ions have lots of places to move, all right? They can hop through the polymer, okay? This is a block copolymer that has chain ends that are useful for solvating anions and cations, but you get some structural stability from the core. Okay, and then you have salt-doped cross-link polymers. So salt-doped cross-link polymers have been explored in the sense that when you cross-link some polymers, they are not susceptible to lithium dendrite penetration. They're just strong enough. So that makes good sense, except for as soon as you cross-link it, the diffusion rates go down. So there are polymer electrolytes, and some of them work. Some of them require that you use warmer environments to have them work. So in Boulder, Colorado, there's a company called Solid Power, and they make solid state electrolytes, not polymers. At least I don't think so. I'm not absolutely certain. But they only operate at 100 degrees centigrade. So, are there applications for solid state batteries that only operate at 100 degrees? If you're from Colorado, you might know. In Colorado, they do a lot of oil drilling. And they monitor temperatures in wells to see what the viscosity of the oil is so that they can know how to heat it or pump it out. And downhole temperatures can be 100 degrees centigrade. So there are batteries that will function quite nicely there, and Solid Power has sold this as an idea. And I have no idea how well they're doing, but they must be doing reasonably well because they've been in existence for about 10 years. One of my graduate students works there. Okay, so I guess former graduate student. All right, finally, of course, salt-doped homopolymer with ionic liquids is the gels. All right, so we know now what a solvation sphere looks like with liquids. With a polymer, you can have what are called Lewis basic and Lewis acidic polymers. And with Lewis basic, then you have components in the polymer that solvate the lithium ion, all right? They're basically electron donors, something like oxygens. Okay, we'll talk about polyethylene oxide in just a moment. All right, if you do this right, then you have a very weak coordination of anions, which means that the anion-cation pair is not hopefully a contact ion pair, which then promotes movement of the lithium or allows movement better. Or you can have a situation where you strongly coordinate the anion and allow the lithium to move. All right, that would be a Lewis acid polymer. And this might be something that accepts anions. So it could be, for example, an aluminum compound. We'll see that coming up in a better example. So these are possible scenarios for lithium-ion movement through polymers. So I have a polymer hanging segment. It could be an anion or it could be a cation. An anion would now allow lithium ions to move. So this is a mobile cation. So it just traverses the individual hanging segments and moves on between polymer chains. And that is in fact very doable. Again, the mobility is dependent on how strongly this hanging segment bonds lithium. Okay. You can also envision that you can move both the cation and the anion along the hanging segment. Is there value in that? Well, no, there isn't, but it can happen because the charge separation induced by the hanging segments is insufficient, and so you get a cluster to move, and we don't want clusters, okay? At least not initially. Okay, still another issue is one that you will run into if you delve to any extent in the literature of polymer electrolytes. Polyethylene oxide is a very common polymer electrolyte, okay? And polyethylene oxide is very nice and can be very highly crystalline. So if it's highly crystalline, what does it tell you about the polymer chains? They pack loosely or densely? They pack densely, right? So then what is my vision of lithium-ion movement in crystalline polyethylene oxide? It's unhappy, it doesn't want to move, it's very stable, let's stay here and go to the local bar. Okay, so in that case, the conductivity is small. The chemical potential inside is low. And if you have regions, and you will always with polyethylene oxide, have small regions that are amorphous at the chain ends. So the chain ends are flexible. I can do this all day, okay? So the chain ends are flexible. As a consequence, the movement of ions occurs where the chain ends are flexible. What that means is that if you use lower molecular weight polyethylene oxide, the crystalline segments will be smaller and the number of chain ends will be higher volume fraction wise, and you'll get some mobility. So this is the idea here, is to either do that or add a small amount of solvent, and the small amount of solvent will probably aggregate at the chain ends. And now if you do this correctly, you'll have pockets of amorphous, and the lithium ion will move through those pockets of amorphous that are solvated. So this is called percolation. Conductivity is high, the chemical potential is high in the amorphous regions. So you can understand, people have looked at this. I might point out, this is not new, it's quite old, but in the context of this course, it's important to present it this way. Okay, polyethylene oxide. EO. So polyethylene oxide is made from ethylene oxide, which is made from silver oxidation of ethylene, and then polymerized. And if you've ever heard of crown ethers, then they look like crown ethers. The oxygens form tetrahedral arrays around the metal, okay, and we're looking to have it move from one point. So these are these segments here, and it's moving to these segments here. That's hopping along the chain. You can obviously see that if I heat this up, the chain segment motion is going to increase. And when it does, the movement of lithium will be promoted. Okay. So you can also add counterions. This is our favorite TFSIA, perchlorate, PF6. All of those also affect the crystallinity. It turns out that you can add perchlorate, and perchlorate interferes with the packing of polyethylene oxide, and it becomes more amorphous or less crystalline, which means that the mobility of lithium ions is important and reduced, and therefore you can get conductivity. As time permits in the course, my group has made some polymers that can dissolve in polyethylene oxide. And while most polyethylene oxide lithium complexes show mobility at 65 degrees, which is the melting temperature, our systems work quite well at room temperature. So, but that's a story for another day. Okay, so we have the fact that the solvation of these ions is pretty similar to what we see with the carbonates, right? So think of the clusters as being representative now of the way ethylene oxide binds. Okay, so we can have intra-chain hopping where it just moves along the chain. All right. We can have inter-chain hopping between chains. And what we really don't want is to have clusters move, but indeed you can have clusters move. Now, if all you have is clusters moving and you can get them to move fast, then maybe that's okay. All right, but all of this requires that the segments move on a continuous basis, which is why a lot of polyethylene oxide derived materials are operated in lithium ion batteries at 60 degrees. I think I mentioned that there was a company in San Francisco that was acquired called CO, and CO had polyethylene oxide polymers, and they worked well enough for the company the CO to convince a large chemical company to acquire them, Bosch, and then Bosch sold them because they couldn't come up with a better system. Okay, so sort of like another schematic to discuss what we've already learned. We have a large diffuse anion that's well solvated, so it's separated from the cation over there. Or we can have it poorly solvated, and then it has a large hydrodynamic radius, and then it interferes with ion conduction of the lithium ion. So if the anion is big and diffuse like the TFSIA, then it doesn't play much of a role. And so that's good. If it's small, okay, like a chloride ion or something like that, then it can interact and form clusters, which then limits diffusion and conductivity. All right, so having said that, why would I use TFSIA, Jeff?
Has a large diffusing radius.
Okay, even though it's expensive?
Yeah.
Why?
Because that keeps your effective cation radius down, which helps diffusion.
I was looking for a different answer when I said that you know. Cost of ownership.
Right.
Okay, so you can envision that people are really, really interested in anions that contribute to diffusivity. All right, and perchlorate is always very useful. Anybody know why perchlorate's not something you want to work with very often? Does it have a lot of oxygens? Does that mean something to you? It's explosive. So perchlorate salts can always explode. Not very nice. Perfluoro or tetrafluoroborate and hexafluorophosphonate are inexpensive, but they have fluorine in them. Okay. This guy is an aluminum anion with 4 nonafluoro T-butoxide, nonafluoral T-butoxide, tetra nonafluoral T-butoxide. What do you think, Jeff? Is that really a diffuse anion? You're right, it is. It's a very diffuse anion. Think it's expensive, anybody? Yeah, it's expensive. All right. Now we have this tris pentafluorophenyl borate. Notice how that rolls off my tongue? It's because I said it a whole bunch of times. Okay, it's a catalyst for something else. It's a Lewis acid. This is a different boronate. And Jeff, can you give us an idea of the cost of these things?
Very expensive.
Very expensive. Okay, so why then, Jeff, would I want to use them?
They're very diffuse and the cost of ownership.
There you go. Fist bump. Cost of ownership. All right, I want to be honest with you. No one will use these really in batteries. Why? Because the cost of making them and putting them in batteries and then to recover them is so high that they are academically interesting, or there's one other reason. This reason is totally unrelated to anything that you know, something I know. It turns out that I can make titanium compounds with these guys, and I can use those titanium compounds to polymerize ethylene and propylene incredibly fast. And so the amount that I need can be parts per million per 100 kilos. So then the cost of ownership is small. But that's not part of this course, all right? Just sort of an aside. All right, so dimethyl sulfoxide. Let's see. I don't believe anybody here has probably been to Seattle. Anybody been to Seattle? Have you ever been north of Seattle? You are from north of Seattle. So when you drive north of Seattle, north of, let's see, what's the town where Boeing builds their, Everett. North of Everett, if you're on the highway, 405, what do you smell? Actually, no. You smell the byproducts of wood processing, and you smell dimethyl sulfoxide. Okay, so it's in the air. It's not particularly toxic, but it's very polar, and so it has a very high dielectric constant. So it becomes a wonderful solvent, in essence, for a battery if it dissolves salt. So you can imagine that it does. It coordinates here. It's showing coordination of potassium to the oxygen and X- to the sulfur, and it would work well with perfluorate and TFSIA or the trifluorosulfonic acid derivative. All right, all of these guys. So cool. What's the problem with DMSO? Well, it freezes at 18 degrees, so you can't use it anywhere except in very hot climes. But it is an example, and it's already oxidized, so it isn't going to be very flammable. It might be something you would mix with a different solvent. Okay, keep that in mind. So now, ladies and gentlemen, boys and girls, here are lists of all sorts of anions that are diffuse. These guys, the aluminum compounds, anionic aluminum, can be a counterion and can be used with lithium salts if they're relatively inexpensive or the cost of ownership is low. Okay, these are borate salts, and they're all interesting only in that people have figured out that they're not coordinating, but no one is going to use them most likely in any kind of battery. But this is a list just because you need to know that they exist. You don't need to know any more than they exist. So this is a sort of like you go to a restaurant menu and you can see all of the very expensive wines that you will never order, but they're there because it's a show-off sort of thing. Okay, so All right, so now solids, solid polymer electrolytes. Sorry, solid electrolytes. Okay, so now our matrix is anionic, and so the anions are immobile. We're only interested now in lithium ion movement. So that's cool because now we don't have to worry about loss of energy because of anions and solvent spheres of anions and so forth. However, as you already know, movement of ions in solids is going to be slow unless you're very lucky. All right, so now you all are here because you know that the investment in batteries is so huge that everybody has looked at some of this, okay? And now there's some materials that have been risen to the surface that are valuable. So we're interested in having a lithium ion sitting in, and remember lithium is very small, and these are oxygen ions sitting next to some metal that you can barely see, and the lithium is moving. And as it moves through a bottleneck. That bottleneck is really what we're interested in. It has to go periodic up and then down, and we need to understand the migration energy, control that by controlling the diameter of the bottleneck, but not making the separation of the anions too large so that the lithium just sits on one and doesn't move. It has to be sort of positioned to move evenly, and we can talk about this in terms of Schottky and Frankel defects. So in the case of a Schottky defect, lithium ion moves from one place to a vacancy, but it does pass by these guys here, these anions, so it's attractive, but it has to get through them. So there's still a barrier, okay? And in Frankel defects, you have these atoms jump through interstitial, so you can go from here to here, but it goes via an interstitial position there and knocks it off sometimes. We'll talk about this in a little more detail just now. But before I continue, does anybody have any questions? No questions, all right. So, ladies and gentlemen, boys and girls, the first step is to understand that you can have different mechanisms that are materials dependent or crystal structure dependent. Okay, they can change. So this one is just interstitial hopping, okay, from one stable interstitial position to another, okay, or you can have it push one from one place to another and then knock it off. And so it turns out that this knockoff thing actually works better, and I'll explain why, okay? And then there's vacancy direct hopping, okay? Moving in and out through vacancies. Vacancies are good. Vacancies are wonderful. The Airbnb of lithium movement. Okay, so the lithium is sitting in an array of oxygens, looks very similar to what we said for polyethylene oxide, and we need to find out what kind of energy is required to get it to move over to the next site. All right, so that's the simplest picture. So I'm going to give you a set of examples, and I am interesting. I am going to suggest that we're going to spend more time on this, and you will get lectures in detail on the individual materials. All right, but this is a 3D network that is one of the very first lithium ion conducting solids, lithium titanium phosphate, LTP. And it's got a crystal structure that consists of phosphate tetrahedra and titania octahedra, okay? In the titania octahedra, the titanium is uniformly bound to all of the oxygens each of the oxygens contributes 1 2/3 electrons. So they're equidistant. It's not really like that, but it's continuum, all right? So, but the important thing is that there are 3 ion diffusion pathways, lithium 1, lithium 2, and lithium 3, all right? And they're interstitial sites. And in this material, all lithium 1 sites are occupied and lithium 2 and 3 are empty. So I have a place to run to, okay, if I want to move. However, I'm so electrostatically happy in one position, I need an activation energy to move, right? So I have to heat it up. All right, so I have a place to go, but I have to be motivated to do that. So statistically, I can do this, okay? And so lithium titanium phosphate has a conductivity of 10 to the minus 6 Siemens per centimeter. This is really low, okay? Really low and not very effective. However, somewhere before 1990, this guy Ono in Japan did some very seminal work. And he found that if he dopes this system with a little bit of aluminum or scandium, and he found at X equals 3, all of a sudden the conductivity goes from 10 to the minus 6 to 10 to the minus 3. 10 to the minus 3 is 1 millisiemen. All of a sudden, we're close to the conductivity of a material that would be like a polymer separator impregnated with a liquid electrolyte. Okay, wow, that's great, right? So in addition, what he found was that people who made lithium titanium phosphate usually didn't make it in a very dense form. And so the conductivity wasn't that great because lithium ions can't jump through space. So when you dope it and sinter it to very low porosity, and also the lithium ion conductivity is proportional to the final density. So this changed what people thought about ionic conductivity in solids. That's why it's seminal. We will spend more time on this because this is one of the supposed holy grails of ceramic electrolytes. There are lots of issues with it, which we'll get to. This now is the lithium aluminum titanium phosphate that Ono developed. And why do I put aluminums in? I put aluminums in because aluminum is 3+. I'm replacing titanium 4+, right? So when I replace titanium 4+ with aluminum 3+, I also will lose oxygens. All right, for each aluminum, I will lose half an oxygen. Or for each 2 aluminums, I'll lose an oxygen. What that means is that as long as the crystal structure is the same, the lithium now has a place to move that it didn't have without the aluminum or scandium. Quick, who would like to use scandium or aluminum? Which is your choice? Can you go out and buy a scandium can? No, you can't. All right, so there's a sort of an idea. All right, so without doping, then the energy to move through the ceramic electrolyte is non-uniform. This is the high, the low, the high, the low, the high, the low, and then over here it's much higher. When I dope it, then I get a uniform energy landscape, so the mobility of lithium is uniform through the ceramic. It's not held up by passport control. Can I see your papers, please? Okay, so that's why it is important to understand the effects of doping. Here's another example. One of the really, really cool and important materials which includes the kind of materials that I mentioned for the company called Solid Power, is this LGPS, lithium, germanium, phosphorus sulfide. In this system, the lithium ion mobility is like 12 millisiemens if it's doped properly. That's 10 times LATP. That means I need less of it to get good ionic conductivity. But it's found that if you replace tin with germanium, the S3-S3 distance changes. And when it changes, the gap gets smaller, and the ability of lithium to move through is impeded by the smaller gap. So the activation energy for conductivity is diminished. So there's a trade-off in adding tin to LAGPS. This material is exciting because it can be pressed into a thin film just by mechanical force. It doesn't need to be sintered. So this is why it's of considerable interest to lots of people, because it's a solid electrolyte that doesn't need high temperature processing. Why aren't we all seeing things like this everywhere? One of the problems is the sulfur. Remember I mentioned something at the beginning of class about water. Water is everywhere. Water is gonna be there whether you like it or not. Even when you use the dry box, which has very low moisture contents, surfaces that you bring in and out will have traces of water. And now this system reacts with water to produce H2S. H2S is rotten egg smell. H2S is really toxic. So it's one of those things that people shy away from. If you want to scale it in production, you have to think about this. I'm going to have workers that are going to be working with this in large quantities, and even if they are even a little bit exposed to H2S, it might be a safety factor. So that is, in fact, one of the reasons why it's not yet a big commercial product, though we may see that change. Okay, so now one of the things that, again, we'll talk about later on is LATP or LATSP, because there's a silicon doped system as well, is reactive with lithium. It gets reduced and gets destroyed. So people have looked for alternatives, and LLZO, as it's called, lithium lanthanum zirconium zirconate, I guess, has a garnet crystal structure, and it has several sites for mobility, okay, lithium 1, lithium 2, and the pathway of lithium movement is very nice, except for the fact that its conductivity is only 0.1 millisiemens in most crystal structures. We will be back with this another day. Okay, so I'm going to finish class now. I was under the impression I would get all the way to lecture 5. I'm actually happy I didn't, because it's a very large and very complicated lecture, which I would rather we do next week. Anybody have any questions? Homework typed, electronically sent, Monday morning, say 10 o'clock. Not really worried if it's noon. Do a good job, that's more important. And on that note, ladies and gentlemen, oh, there's a chat. Let's see what that is. Aluminum, okay, she had an answer.
The homework due Monday morning or Friday morning?
Friday morning.